Okay, now the third corollary of the result that that is hiding underneath this board. Let f, a polynomial with coefficients in f, suppose irreducible factors of f, the polynomial f, are separable. They don't have any repeated roots. Let K be a splitting field of f over f. Then the number of elements of the Galois group of K over f is equal to, let's see, so these are automorphisms of K that fix f, right? Automorphisms of K that fix f. Now, if you look at the following picture, f with identity to f, K, splitting field of f, polynomial f over f, and then K here as well. And now, well, what's identity star of f? That's just f itself, right? Applying identity to the coefficients of f, you get f. And now, okay, so what is this result telling us? It's telling us that the number of isomorphisms from K to K which extend identity, the number of those is exactly equal to the degree of K over F. So here the splitting field is called E, there is called K, doesn't matter. But the point is that the number of isomorphisms from K to K, the number of automorphisms of K, which extend the identity map on F, which fix F, the number of those is exactly equal to the degree of K over F. Right? The key hypothesis is that the irreducible factors of F are separable. So the number of automorphisms of K which fix F is exactly, or in other words, the number of elements of the Galois group of K over F is exactly equal to the degree of K over F. Okay, so this what we get is that if K is a splitting field over F of a polynomial whose irreducible factors are all separable, then the degree of the order of Galois group of K over F is the same as the degree of K over F. By the way, what happens if we drop this separability hypothesis? Maybe just add that as a remark. If we drop the separability hypothesis, then, well, if you look back at the previous video where we proved this theorem, remember actually there was between these two statements, between these two assertions, there was an intermediate assertion which said that, so it didn't have this hypothesis of the reducible factors of F being separable, and in general it said that the number of sigma hats is at most E over F, the degree of E over F. Okay, so now if we drop that, the hypothesis that our polynomial F is separable, then, well, the number of elements of the Galois group say that the number of isomorphisms from K to K, which fix F, which which extend the identity map on F, that number will be K over F. This is now at most that degree. K over F. Yeah, very good. So the number of elements of the Galois group of a splitting field is always less than or equal to the degree of the extension if the splitting field happens to be the splitting field of a polynomial whose irreducible factors are separable. Well, in particular, if it's the splitting field of a polynomial with no repeated roots at all, then, sorry, I'm just trying to make sure that we don't lose the camera, then the number of elements of the Galois group is exactly equal to the degree of the extension. So for instance, if you look back at this example that we had, when we looked at the Galois group of C over R, well, is C a splitting field over R? Yes, it is. It's the splitting field of x squared plus 1. So then maybe I can erase these statements because we're done with it. So C, so let's maybe include this as a quick example. C is the splitting field of x squared plus 1 over R. Well, this polynomial over R, it's irreducible, and well, the characteristic is 0, it's separable. So the number of elements of the Galois group of C over R is equal to the degree of C over R. What's the degree of C over R? Well, it's 2. One way to see it is that, well, C is R adjoint I, and the minimum polynomial of I is of degree 2. Or you could just go back and, from earlier things we know, that C is a two-dimensional vector space over R. Okay, so this degree is 2, and so the number of elements of the Galois group of C over R is 2. But remember, we already found 2 elements in that Galois group. Identity, well, identity is a group, identity always there. Identity and complex conjugation. These 2 things are in this Galois group. Well, the Galois group only has 2 elements, so those are the only elements. So the Galois group of C over R is equal to, in fact, well, identity and complex conjugation. It's a group with 2 elements. It's isomorphic to Z mod 2. Okay, very good. I think, actually, maybe let's do another example too before we stop.